A, we'll start with Hannah. No. You wrote no, and I agree with you. How's that? Is that good? All right. B is just a statement about rate of change that you were to read. You could also consider this notes. You might want to use a little highlighter like this when you go through your notes and when you read your textbook. Okay. C, find the average rate of change in the number of male drug overdose deaths in the U.S. between 1999 and 2015. So, Hazel, what do you have there? Does that look right to most of you who did it? Okay, and what you get for your answer there? Huh, I don't have that. In mine, oh, I see right here. 2015, oh, I know what I did. I did it for all of them instead of the males. Okay, so what did you get again? 21,000. 699 over 16. Okay, and usually, so this would represent how many deaths occurred over 16 years. We always want to reduce this to what we call a unit rate, where we have the number of deaths per year. Okay, so we need to do one more step here, and we need to do this division. Did anybody get that far? 0.1875, I do want the decimal, because it's in hundreds of thousands. Okay, so when you say 0.2 of 100,000 or 0.18 of 100, it's a lot of people, right? Okay, so this would be 1356.1875, and if we put the units on that, that's the number of male deaths per year. All right, so on average, so when you interpret this, on average, the number of male deaths due to blah, 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 from blah, 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 increased by 1,300 approximately, and in this case, when you're writing a sentence, we'll just round up. Okay, so on average, because we're looking at the average rate of change, okay, the average rate of change over that time doesn't mean that every single year there was a difference of 1,357 deaths. Okay, now this is a pretty serious problem, as we all know right now, not only in our country but in other countries. So this table goes up to 2015. So when we get this estimate here, down here, I don't believe we don't have 2018 in, but I think I might be able to get 2017 relatively soon, so we can do a comparison. Okay, so one of the reasons we look at variables is we try to find a relationship between them. We're not looking at the graph of these right now. Let's see if I have the graph of these opioid deaths. That would be in my GeoGebra folder. Can't remember what I did back in December and January. So still January. Okay. Do you see lesson 2 domain? I don't see opioid deaths. That doesn't look like a GeoGebra file though. I think that's just the table. Okay. So it might be interesting to look at this table and see, does it look like it's a linear or exponential? What's happening here to these death rates? Okay, so this question is the type of thing you do in section 2.3, which is 2.1 and 2.2 just introduce you to like lines and how to write lines and graphs of lines, and then you put it all together. And in this particular case, you're given a situation, you have to convert it to 2 points that would be on a line, and then find the slope, which you've already found right here. Here's your slope. Right here, here's your slope. So you've already done that part. Let me highlight that. There's your slope. That's the slope of the line between those 2 points. So those 2 points would be 0 if you let your t value be number of years after or since 1999. Your first point for 1999 would be 0, 11,258. And then your last point, 15, what would be the t value for 15? For 2015? It's number of years after 1999? 16, and then the number of deaths for that year was 32,957. Okay, so whenever you get an equation for a line, you have to find its slope. You've already done that right here. So the slope is, let's call it 1356.1875 times t, not x. T is your input variable, plus your intercept. It's right there. There's your y-intercept, 11,258. So check your work and make sure you have that. Now we want to predict the deaths for 2018. So what's the t value for 2018? What's the t? How many years after 1999? 19. So all you do now is you plug in 19. You take 19 and you plug it in right here for t, and you do that multiplication and addition. And someone want to give me the answer for that? Okay, I'm going to call it 37,026. Okay, does that seem right to people? Okay. All right. So this was an important activity for you to do because you're being introduced to one of the topics of today called the average rate of change. It reviews how to find a equation for a line given information. You have to extract that information and create the pieces for your equation, like your slope and your intercept. Okay, so it's clear that I haven't been clear, I guess, on what homework's supposed to be for this class. So when you look at lesson number 3 today, you notice that you have 3 sections up here, 1-3, 2-1, and 2-2. That means you will have mom homework on 1-3, 2-1, and 2-2. So when you go to do the homework tonight or tomorrow night or early Friday morning, whenever you do it, you need to do those 3 sections. Okay, so let's take a look at where you also, for those of you who are new to this class or new to, like you haven't had 107 with either me or Caitlin, some of this might be a little bit new to you. So when you go to the very end of lesson 3, you will see your homework listed. Oops, that wasn't very nice of me. And your homework will always tell you what the expectations are. Notice you have to always complete, oops, I thought I had my highlighter on. You always have to complete and be prepared to discuss the preview exercises for Friday, which is lesson number 4. And then your homework is all of this stuff about taking notes from your book, okay? And please do the homework assignment in Mom found on our Moodle site for 1-3, 2-1, and 2-2. Now remember, sometimes I told you to be looking for additional problems, and I didn't have them listed here necessarily. So make sure when you look at your Mom's site, you heard it, so okay, yeah, I do. Thank you. Keep reminding me about recording. Okay, so rate of change will describe how the output quantity changes. That's your dependent variable. So if we were looking at something like distance versus time, and we would be looking at how the distance changes per unit of time. We tend to call that speed, right? How the distance changes per time. So how the output quantity changes in relationship to your input quantity. The units on a rate of change are written as output units per input unit. So let's say we were looking at kilometers and kilometers over seconds. We would be talking about kilometers per second as our units on the average rate of change. All right. We recognize this formula as a slope of a line because when you're looking at a line, what can you say about the average rate of change for a line? Any walking along a line from one point to another. What can you say about the average rate of change? It's constant. It never changes. Not like our opioid problem where the average rate of change from year to year. So with the line, it never changes. But other graphs, curvies, right? When we go from one point to another, the average rate of change is not going to remain the same. So let's take a look at this particular graph. It's a parabola, x squared minus 2x plus 5. It doesn't have any real number zeros or x-intercepts. It would have complex. Remember, we covered those in 107 because it doesn't cross the x-axis at all. So let's find the average rate of change between the numbers -1 and 6 inclusive. So remember, for some of you who are just learning this, this is an interval. This is interval notation, and it talks about all x values less than or equal to 6 and greater than or equal to -1. Where's your chair, Gary? Oh, do you want me to bring a chair over? Okay. Oh, okay. All right, so what we're looking at now is you should go down to your x-axis and you should say, okay, I'm at -1. And unfortunately, your graphs didn't go all the way out to 6. I noticed that this morning. So you can just pretend, go out a little bit further. Your graphs only go up to 5. You can just go out a little bit further, okay? So this is what I'm interested in, this interval right here. So those numbers, -1 to 6, talk about all x values in that interval. Okay. So when we use function notation, notice we don't say y equals, we say f of x equals. So here, the only difference between using functional notation and what you're used to seeing for like the slope of a line is we used to use y2 take away y1 divided by x2 take away x1. When we use functional notation over an interval, you look at the y value at b, take away the y value at a, called f of b minus f of a, and then you look at the difference between b and a. So the notation changes, but the idea is exactly the same. So let's take a look at this. We want to know the average rate of change, so we're going to call it ROC, average rate of change. And so we want to do f of 6 take away f of -1 divided by 6 take away -1. So to find f of 6, I've got to put, if I can tell from my graph, sometimes you'll be able to tell, but unfortunately on your sheet you can't. So you go up to your graph and you see where does it intersect. And I believe it's 29, but let's take a look. Could be 28. How do I know what f of 6 is? I plug it in. 6 squared minus 2 times 6 plus 5 is 36 minus 12 is 24, 29. Okay, so that's 29. And f of -1 is -1 squared minus 2 times -1 plus 5. That's 1 plus 2 plus 5 is 8. And over here, you go up to your graph and you're at a height of 8. Okay, so that's 29 take away 8 all over 7, which for once in this class we get a nice integer for an answer, 3. So the average rate of change is 3 to 1. Now what does that mean? That means that if you connected those 2 points right here with a line, what does the 3 represent in terms of that line? Slope. Okay, it's the slope. Because from -1 over to 6 would be a change in your x of 7, and from 8 to 29 would be a change in your y of 21. So 21 divided by 7 is the slope of this line. Okay, that's the average rate of change. So let's look at the shape of that graph. We call that a parabola that opens upward, right? If I was looking at the slope of a line that connected any 2 points along here, any 2 points, any 2 points on this parabola that's shaped this way. Would that line be above the graph or below the graph? So what I'm asking is pick any 2 points on here. Let's pick another point. Let's say we took this point here and this point here, and we connected that with a line. Suppose we took this point here and this point here, and we connected that with a line. If you could imagine just kind of walking around that upwardly shaped curve, that bending curve, would that little line segment be above the curve or below the curve? Above. Okay? That's always going to happen when you have these curves that open upward. Now, I'm going to give you a name for this line, and you're going to hear this over and over and over again when you get to calculus. So I wanted you to know the name of this line now. When the slope of this line, it's called the secant line. We call that the secant line. Okay, just so you have the language when you get to calculus. This is called, all of these lines are called secant lines. So this is a secant line. All of these are secant lines. So when you have a curve that's bending upward, all of your secant lines are going to be above that curve. The curve's going to be below it. And what you're going to do in calculus is you're going to make these points come close. I'll wait till you get to calculus. Stop. All right. But you will hear secant a lot. Okay. All right. Everybody okay with finding the average rate of change on an interval for any kind of curve? Any questions? Mariah, you got a question? Oh, Barry, sorry. I'm going to do this. Sorry. Okay. All right, so let's do a quick review of linear functions. All right, linear functions have a constant rate of change. The graph of a linear function means I have to talk fast, right, is a line. Ooh, let's see how many, if we can get from this class, all 3 forms of the equation for a line. What's the one everybody can say as a chorus effect? See, you even did the chorus. I love it. mx plus b. So this is called slope-intercept form. Okay, slope-intercept because you have your slope m and your intercept b. Okay, now the form. I'm almost afraid to ask. Gary? X, y equals x. That's a particular line, and that's in that form, right? So y equals x would be a line in that form, a very particular line. I'm looking for general equations for lines. Yep. Jackson?
Minus y2 equals mx minus x2 plus b.
Okay. So y minus y1 equals m times x minus x1 plus b. Doesn't matter what you call the subscript. All right. That's called your point because you're given a point, any point on a line, point slope form. All right. The one everyone forgets. The one that's really easy when you want to graph and you just use your intercepts. The intercepts. So no one's going to remember. Ax plus by is your constant. So if you had something like this, 2x plus 3y equals 6, if I gave you a line in that form and I said to graph it, boom, you say let x equal 0, y is 2. Let y equal 0, x is 3. You got 2 points, quick graph. Okay, so this is called just the standard form of a line or your general form. Okay, very similar to ax squared plus bx plus c is 0, similar to that. Slope, we know, is the change in our y values over the change in our x, y2 minus y1 over x2 minus x1, just like what we've been looking at with the average rate of change. Again, that little triangle is the baby delta. It's a Greek letter, means change in. Change in your y values. Okay, so what were the units for the slope in the drug overdose program? What would be the units? The y units, the numerator dealt with what? What kind of deaths? What kind of overdoses? Drug overdoses. For who? Male. So number of male, so it was male drug overdoses in the US. And what was our bottom denominator? Time in years. Okay, years. All right. Yep, thank you. Per 100,000 males, right. All right. So the slope represents your average rate of change. Same thing. ROC. All right, so let's quickly find the equation for this graph. I'm going to give you a few minutes to do that on your own, and then we'll take a quick peek at that. Do we have a table that wants to volunteer about which is which here? Yeah, Jackson? All right, that's going down. I guess they went up really quick, but they didn't check with each other to see if there's consensus. Okay. Barry? You think it's the opposite? You think this is the ball being dropped? I guess Jackson dropped the ball, huh? Ball drop. Now, see, if I hadn't had you before, I would never say that to you, all right? But Jackson and I, we go way back, so I can say Jackson drops the ball, okay? All right. So, Barry, what were your thoughts, or what did your table talk about when you were trying to decide which graph went with which pitcher? The plane is going to slow as it reaches. And how can you tell about the slowing here? Okay, so the slope is decreasing. That's an interesting word to use when you're not looking at a line, isn't it? So basically what you might be considering is like 2 points on this curve, right? And thinking about the slope of the secant line that connects them, right? And as you get closer and closer here, that secant line, the slope of that secant line is getting less and less, yeah? Okay, and what about the ball drop? What happened to the ball drop? What's the change in the height over time right around the beginning? How is it? Right here. How would you compare that slope compared to this slope? It's less, right? So when we talk about the change of height over time, we're talking about speed, right? A velocity in this case, because the velocity is the speed pointing downwards. So initially, this ball is dropping slower, and as time picks up, the ball plunks right down to earth, right? Gravity acts upon it, and it hits the ground after 3 seconds. All right. Whereas, thank goodness, the plane doesn't arrive like that. The plane has a very steep drop here, right? In the first few intervals, a very steep drop. Or the speed that the plane is arriving continues to slow down to a gentle landing. Okay, so how we talk about increasing and decreasing can change based on the shape of the graph. Is it curving up, bending upward like this, or is it bending downward like this? So look, we have 2 increasing graphs and 2 decreasing graphs, but they're both increasing and decreasing in different ways. So let's talk about concavity for a minute. So this might be new for a lot of you. So again, if you're interested, I have all kinds of markers and colors and stuff like that I can put on your desk. I think color helps a lot when you're reviewing stuff. So we say that a concave up curve bends upward as we move left to right. It bends upward. And this means your rate of change is always increasing. So let's see if we can identify which of these curves out of the top 4 are concave up. Okay, so would you say that this is bending upward? Yes, so this is concave up as we move left to right. So this would be concave up. Just think of a teacup. That's what I think of. Teacup, concave. If you like trace the outside of a teacup, right? It would be concave up. Which other of these 4 pitches is also concave up, bending up with the bottom one right here, right? This one is concave up. It's the other side of your teacup. Okay, which leaves the last two pictures as our concave down pictures. So let's pick a different color. This is bending downward. It's increasing the whole time, but it's bending downward. So this is concave. Whoa, turn that into a straight line on me. Let's try that again. Concave. It's bending downward. Okay. This is concave down. And this one is also concave down. And the rates of change for concave down graphs are always decreasing. Now you might say, wait a minute, decreasing? Really? So let's take a look at that. Am I going to lesson activities right now? No. Okay. So I wanted to show you with these, you see how I did this right here? I put the points in with ROC beside it. So notice each one of these are just changing by 1. So what's the rate of change between this 0.09 and the 0.18? What's the rate of change? Well, all you have to do is literally look at the difference between these numbers. That's your numerator, because these are always going to be 1 here. So the rate of change between 0.9 and 1.8, that rate of change is 1 to 1. So that's rate of change is 1. You go down 1, over 1, negative 1. Okay. What's the rate of change between 1.8 and 2.5? Ooh, let me bring back in this other idea I was starting to tell you. So if I connect those two dots with a secant line, is that secant line above or below? Below, because it's concave down. You'll always be below the curve when you're concave down, above the curve when you're concave up. Okay, 8 to 5, what's our drop? From 1.8 to 2.5, we got a drop of 3 for that one tick of 1 second or 1 minute, whatever the time is being measured in. So that's -3. And from 2.5 to 3.0, you're dropping 5 units for that 1 unit of time. So that's -5. Okay. So this is the tricky part. We say the rate of change is decreasing because your numbers, your rate of change here is, no, it's decreasing. -1 to -3. Remember, here's -1, here's -3, here's -5. As you move further away from 0 in any direction, you're decreasing, yeah, to the left of 0. Even on the right, if you're over here at 5 and you go from 5 to 3, you're decreasing. Okay, so that's the tricky part. You can't just look at the absolute values of the numbers. You've got to think about, am I becoming more negative? If I'm becoming more negative, then I'm decreasing. My rate of change is decreasing. If I was the other way around, I would be increasing. So let's take a look at this next picture, and let's look at the rate of changes here. We know our change between our time is all 1 second all the way down. So let's see, we go from 0.9 to 1.4. Okay, and if I connect those 2 points with a secant line, notice the line is above the curve. It almost looks like it's exactly on there, but it's just above the curve. So that's what? A decrease of 5, right? And then from 1.4 to 2.2, we go down and over. 1.4 to 2.2, we go down 2 and over 1. Okay, and again, if we connected those 2 points, we'd be above the curve. From 2.2 to 3.0, we go down 1. So again, you're above that curve. It's just the width of my pen here makes it look like I'm right on there. So what's happening to my rates of change as I go from -5 to -1? Are they increasing or decreasing? increasing. My rates of change are increasing. This is concave up. My rates of change are decreasing. This is concave down. You could do a similar thing on your own with these two graphs here. I'm not going to do it for class, but you could just sit right over here and do your X and Y values. Pick a couple on this curve, look at your rate of change, and do the same thing here. But all you also have to do is look at the picture when you form that secant line right here, right? When you form that secant line between those 2 points, it's above the curve. That means your rate of change is increasing as you move right to left. Yeah, Mariah? Yes. Yeah, it's not a silly question at all. Yes, your function is decreasing, and anytime you have a decreasing function, you will have negative rates of change. Anytime you have an increasing function, you will have positive rates of change. Okay, good, because I was getting ready to compose an answer to whatever question she was going to give me, so I don't have to think too hard then. Yeah, Barry? Shane? What? Oh, it's 2-1, not 2-2. Oh, okay. Thank you. So this is -3. Yep. Okay. Anybody else? All right. Yep. Go ahead, Barry. It's the slope. This is the slope of each of those lines. Those secant lines, these are the slopes, right? These are increasing numbers. These are decreasing slopes. It is becoming less steep. I understand, right. There is this kind of idea here that you have to think about not just one individual rate of change, but think about what's happening to all of them along that curve. And yes, these heights are getting smaller, so because we're thinking absolute value in our minds, because we see the height, we're thinking, oh, this distance is getting smaller, so my rate of change must be getting smaller, right? But our rate of change is actually increasing. I know it's a weird thing. Yeah, it's a strange thing. It is strange, I think. Okay, so this idea of concavity, well, you'll be hearing a lot about concavity in your calculus class. Okay, so here's a graph of a cubic, okay, because it has a degree of 3. It has one hill and one valley, has 2 relative extrema, and that's what we call relative max and relative minimum points. Our book doesn't use the word relative like your 107 book does. It uses the word local. So all the same thing. This point right here at 2.8, 2.8 is called the local max for maximum. The point -2, -8 is called the local minimum. Now in 107, you would have called that relative max and relative min. Okay. If we talk about those points generally, we say local extrema. The A at the end, extrema, is plural. So the local extrema would cover both of those. These are not absolute maxes and absolute mins because this graph continues on to positive infinity as x moves towards the left and goes down to negative infinity as x moves to the right. Okay. Whenever your right hand behavior is going down, you'll know that the coefficient in front of your highest degree term is always negative. That's from your polynomial work last semester. All right, so with this particular graph, we want to identify what intervals will our function be increasing and decreasing, and over what intervals is our function concave up and concave down. All right, so as we move left to right, if I trace along this curve here, as I move left to right, what's happening to my function? Am I increasing or decreasing? Decreasing. So I'm starting, remember, I'm starting way out here, and I'm way up here in the sky. I'm starting at negative infinity, and I'm moving in towards -2, and then my decrease stops. So I need to record increasing intervals and decreasing intervals. Intervals are always over x values only. So I'm decreasing from negative infinity, so I use parentheses, up to -2. And guess what? We talked about this in 107. We do not enclose -2. We use open intervals whenever we talk about increasing and decreasing. Because I don't know at -2, am I increasing or decreasing? I don't know what the heck I'm doing. I'm kind of bottomed out right there, right? Okay. Where else am I decreasing? What interval am I decreasing on? Can anybody tell me in interval notation, Rob? All right, how do I write that? Yeah, how do I write it in interval notation? Yeah. Okie dokie. So, yeah, so here I'm decreasing from here to here, forever and ever. And whenever you have two intervals, you put them together with the fancy union sign like that. Okay. Increasing. Let's take a look at increasing. From where to where? -2 all the way to +2. Boom. And they keep turning that into a straight line on me. Okay, but from -2, as I move from -2 to +2, my y values increase, increase, increase. Again, open parentheses. All right. All right, now concavity. Concavity. So let's take a look at this. Can anybody tell me the interval on which this graph is concave up? The happy concave up. Concave up. Let me write it. Concave down. So what does concave up mean? That our rates of change are increasing. So if I took 2 points here and I connected it with a line, would the slope of that line be a very big negative number? And then what's happening to that negative number as I come down here and I get close in here? What's happening to the slope of that secant line, that rate of change? It's getting close to what number? 0, because the line right there at that point would be horizontal, have a slope of 0, right? The tangent line. So you're going from small numbers, because don't think absolute value. Let's say the slope here was like -100, and the slope here is maybe like -1/2. So you're becoming less and less negative. So your rate of change is increasing all along here. Your rate of change is increasing. So as we move all along here, let's take a red. So as we move all along here, our rate of change is increasing. All right. So we're going from what? -infinity. And right now we're at -2. And then what happens from -2 as we move up to 0? Is our rate of change increasing? Yep, it's increasing. But where does it stop increasing? The rate of change stop increasing. Yeah, it actually stops at 0, because now your rate of change, this graph is still increasing, but the rate of change is going from a very big positive number to a smaller positive, until we get the top here. And that's what you're going to learn in calculus, that you're going to talk about the slope of the line at that point, the tangent line at that point, and it's always horizontal, 0. And then we go now from, we're going to be increasing again, decreasing, because we're going from a small negative number to a very large negative number. Now, finding that point right here where your graph goes from concave up to concave down can be tricky sometimes. And the best you can do is just estimate it. You won't always be able to exactly pinpoint it. When you get to calculus, you will have a calculus method that will always tell you where that point is, where your graph changes from concave up to concave down. But you have to wait till you get to calculus. For now, you just do a visual inspection. So we say our graph is concave up from negative infinity to 0, right to there. And then we have a transition, right? At 0, we're going to go from being concave up to concave down. So 0 to positive infinity, we make our transition. So those are the intervals where we're increasing and decreasing, and we're concave up and concave down. Bless you. All right. So real quick here, what does a function that's not increasing or decreasing look like? Well, here's a straight line. Am I increasing? Am I decreasing? How about this one? I heard someone say horizontal, right? A horizontal line is neither increasing or decreasing. Horizontal. So this is, whoops, I'm in the wrong spot. This is to give you a little help with, give an example of, which I love to do. I might say, give an example of a function that's neither increasing or decreasing, and you would put something like this down, f of x equals 2, any horizontal line. How about a function that's neither concave up or concave down? F of x equals x, right? Your identity, your parent function, your baby linear function. Sometimes it's hard to locate when the concavity changes. Calculus will be very helpful there. Okay, so this is part of your lesson activity, but you do this on your own later. I'd like you to get going with these different scenarios here. Please read the instructions. I'm asking you to show the intervals that it increases, decreases, concave up, concave down. Okay. So you're going to draw different scenarios. There's no answers in the back. You can either talk about them as a group, and then you could have me come over and check it. You can do them individually and have me check it. You could use each other, and if you all agree, most likely it's right. Okay? So this is your activity for today.